Hello and welcome to helpyourmath.com. In this video, we are going to look at sketching graphs of quadratic functions in the form f of x equals ax squared plus bx plus c. I call it standard form. I think some other people might call it general form. And we're going to sketch the graph by finding the vertex and the intercepts of the graph. Before we get to graphing, let's just review the various forms of quadratic functions. And before we get to that, a quadratic function is a polynomial function in which the largest exponent of any term is 2. So we saw the kind of general case, and we'll look at the three different forms, and we'll notice that the largest exponent we see in any of the three forms would be a 2. So the first up is standard form or general form, which was on that title slide. With this, we would say f of x equals ax squared plus bx plus c. And then we have some rules about specifically a. So a can't be 0 because if it's 0, well, then it's not a quadratic function because we don't have an x squared term anymore. Vertex form, sometimes known as function form, also sometimes known as standard form, is of the form f of x equals a times x minus h squared plus k. And we like vertex form because we can quickly identify the vertex of the graph. And lastly, we have factored form. Factored form is f of x equals a times x minus x sub 1 times x minus x sub 2. And you might be saying, wait a minute, you said that the largest exponent we would see is a 2. Now I saw that in the first one, and I saw that in the second one, but I don't see it in the third one. First of all, great observation. Second of all, it's because it's factored. If we were to distribute and multiply and rewrite this, we would end up with an x squared because we would multiply the x by the x, and that's how we would get x squared. In factored form, x sub 1 would be a number and x sub 2 would also be a number. Okay, so all three of these are very common forms that we use for quadratic functions. Let's talk a little bit more about the graphs of these quadratic functions, starting with, no matter which form it's written in, if we have a quadratic function, the graph of it is called a parabola. Again, it's called a parabola. I know the emphasis can be a little bit weird. Parabola. The graph of any quadratic is called a, say it with me, parabola. We're going to write in parabola. And what does a parabola look like? Well, it might look like kind of like a letter U. It's a nice smooth curve. And the nice thing about quadratic functions is they all have this shape. So no matter what quadratic function it is, it has to be this smooth curve where it's going down, it's going down, it's going down, it hits the bottom and it goes back up. The only exception is that it could be flipped upside down. It could be reflected, in which case it would look like, let me try to draw it over here. It might look like this, where it's going up, it's going up, it's going up, it hits the vertex and it goes back down. That point that we see where it switches direction, that is that point that's called the vertex. It's a pretty important point because if we ever get stuck and we are on a test and we're like, oh my gosh, I totally forgot every single thing about quadratics in the world. If you can remember that the shape is a U, maybe you can be like, oh yeah, I need to find the vertex. The vertex will be the most important point out of all of the points on the quadratics. That minimum point or maximum point is called the vertex. So if the graph is opening up, then the vertex is a minimum, right? It's the lowest y value on the graph, the smallest y value on the graph. And if it's opening down, then the vertex is a maximum because it has the largest y value out of all of the y values that we would see on that graph. If the parabola opens up, then there is a minimum. And if the graph opens down, then there is a maximum. The graph is symmetric about a vertical line that passes through the vertex. So sometimes we might use this, and this thing is called the axis of symmetry. And what we could see is if we just drew like a vertical line just through here, the fact that it's symmetric means that if we were to fold it and if I was able to draw the graph better, it would fold onto itself, right? That's the idea of symmetry about a line, is that if we were to fold it, that one looks better. If you were to take that, the left side and squish it over onto the right side, those two would match. It is a vertical line And so since the axis of symmetry is always a vertical line, it's going to be of the form x equals, and the variable we actually use for the x-coordinate of the vertex is h, so I'm going to switch to that. Usually if I'm just talking about a vertical line in general, I say x equals a, but just because when we are dealing with quadratic functions, we call the vertex h comma k, I'll just say x equals h. Okay, so let's take a closer look at standard form. This is I switched it from f of x to g of x. The f and the g, those are the names of the functions. So I can use them, this is just like my new function and its name is g. Looks a lot like f, but that's okay. All right, so what information does standard form or general form tell us? Well, the coefficient of the first term, that's sometimes called the leading coefficient, that's that letter a, it tells us two things about the graph. First of all, it tells us whether it's going to open up or down. The graph will open up if a is positive. So if a is positive, then the graph opens up. We have this thing here. If a is negative, if a is less than 0, then the graph will open down and we'll have that frowny face. So that's the first thing a tells us. Second of all, it tells us whether the graph has a stretch or a shrink, or if it has neither a stretch nor a shrink, which is also a possibility. So that's if a is not 1. If we see 2x squared, negative 1/3 x squared, then the graph will have a stretch or a shrink. If it just says x squared, blah, 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 then there is no stretch or shrink because a is 1. Or if it's negative x squared because the coefficient would be 1. So when we're looking at whether the graph has a stretch or a shrink, we don't necessarily care about the sign. The sign tells us whether the graph opens up or down. What we do care about is whether it's 1 or closer to 0 than 1 or further from 0 than 1. So the way we say closer than, compare things to 0 is we use the absolute value. I don't want to scare you with the absolute value. It's just like we don't care what the sign of the a is. That's why we say absolute value. If the absolute value, so just the value that's in front, regardless of its sign, is greater than 1, then the graph will have a stretch. What exactly does a stretch look like? So if a standard parabola, if we just have x squared, maybe it looks something like this. A stretch would actually be like a little bit skinnier. It's like if you reach up and stretch, you're bringing your arms up, you bring them close together. That's the idea of a stretch. So it might be a little bit skinnier than the regular if we just had no stretch or shrink at all. We can think about that because if that number is bigger than 1, you're not only squaring this number, but then you're doubling it or tripling it, making it times 4. So the numbers, the y values get bigger faster because not only are you squaring them, but then you're also multiplying them by another number bigger than 1. And then what about if a is smaller than 1, but still bigger than 0? So we just look at that absolute value. What if it's less than 1? Then the graph has a shrink. And that means that it's going to take more work because now we're multiplying it by something that's less than 1, which makes the numbers increase at a slower rate. So does not have a stretch, it has a shrink. So the shrink would be a kind of like a wider graph. And this one I'm going to have a hard time drawing. Let's see what I do. Oh, that wasn't so bad. So there's my shrunken parabola. Okay, so a, very powerful number here, tells us those two things. Something else we can pretty quickly determine from this form is the y-intercept. The y-intercept, remember, of any graph, that's when you plug in 0 for x. And if we were to plug in 0 for x in this graph, the first term goes to 0 because we have 0 squared times something. The second term goes to 0 because it's being multiplied by 0. That leaves us with the third term. So the y-intercept, when we're in this form, would just be 0 comma c. Something else that we would probably want to find are the x-intercepts. Those are probably going to be more work. For the sake of this video, we are only going to look at quadratics that are factorable. So we remember factorable, that's target product, target sum. We look for that winning combination, and then we would factor from there. Then we set each factor equal to 0. We'll see examples of those. But we would also want to find the x-intercepts that will tell us 2 more points on this graph. So far we have the intercepts, but those are the only points. Very important here is we want to know the coordinates of the vertex and then the axis of symmetry. For the coordinates of the vertex, when we're in this form, we can use a formula, and this is a formula that's consistent, for this form. This is not something I just was like, what fun formula can I come up with today? No, this is a standard formula for finding the x-coordinate of the vertex. And we would say the x-coordinate of the vertex is negative b over 2 times a. So first up, we already have the negative. It's built into the formula. Then you're plugging in values that might be positive or negative. So you have to just be really careful about what you're plugging in and just counting the number of negatives. If you count, so we could have up to 3 negatives because the negative is given. B could be negative and A could be negative. That's 3 negatives. Therefore, the x-coordinate is negative. If only either A or B, but not both, is negative, that gives us 2 negative factors, in which case the x-coordinate is positive. If both A and B are positive, then the x-coordinate would be negative because that negative that's part of the formula would be the only negative, thereby making it negative. So not only is that the x-coordinate of the vertex, this is also the equation of the axis of symmetry. Remember the axis of symmetry? It's x equals that x-coordinate of the vertex. This is it right here. Boom, done. Now, once we know the x-coordinate of the vertex, now we can go and plug into the function to figure out the y value of the vertex. So we would take whatever value we get for x and plug it into the given function. Sometimes we say that the coordinates of the vertex, so I said before we use hk, but here that's not really helpful because we don't have those variables. So we say it's x, comma, g of x. And that's where you go in, or we might say it's negative b over 2a, comma, g of negative b over 2a. To me, this looks a lot scarier than what it really is. It really isn't as scary as that. Let's take a look at an example before we get to the graphing. So just given this function f, we're just going to talk about all of the things that these little open circles would provide for us. So first of all, what I'm going to do is label a, b, and c. And I'm going to say a is 1, right? When there's no coefficient shown, there's an invisible 1. And b is negative 12, and c is positive 11. Okay, so once I've identified a, b, and c, first of all, we're going to start with, well, a. A is going to tell us those 2 pieces of information. The fact that a is positive means the graph will open up. So since a is greater than 0, the graph opens up. I'm just going to do this. And then because a equals 1, there's no stretch or shrink. It's just going to be a regular standard quadratic, no stretch or shrink. Okay, so we've exhausted most of what we're going to use a for, except we are going to visit it again and again. So I guess we haven't totally exhausted it. Next up, let's find the 3 intercepts. Well, hopefully there's 3. 3 intercepts. First, the y-intercept. So that's where we would plug in 0 for all of the x's that we see. And that's going to leave us with, well, the first term cancels, the second term's gone, 11. I always like writing my intercepts as ordered pairs so I don't make any mistakes with those and so I don't get confused. There's a point, I can graph this point. The x-intercepts, I'm going to use that a, b, and c that I found, and I'm going to say my target product is a times c, which is 11. I forgot the c. A times c, which is 11. And the target sum is b, which is negative 12. 2 numbers that multiply to 11 and add up to negative 12 would be, let's see, negative 1 and negative 11. Since the leading coefficient is 1, I can plug those right in, and we end up with x minus 1 times x minus 11 equals 0. Here's that factored form in action right here. And then we're going to set each one equal to 0. If I set x minus 1 equal to 0, I get x equals 1. If I set x minus 11 equal to 0, I get x equals 11. So now I have 2 more intercepts. I have 1 comma 0 and 11 comma 0. And I think that's all the vertex. We haven't found the vertex yet. Just kidding. Okay, so now the vertex, I'm running out of space here. I'm going to go up here. Boop, 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 boop. For the vertex and the axis of symmetry, which I'm just going to call A of S, just because I'm lazy, we're going to plug in negative b over 2a. So we're using x equals negative b over 2 times a, because that's what we plug into. So for our example, we have negative b is negative 12 over 2 times 1. We have two negatives here. So since we have two negative factors, we're going to end up with a positive. And then in the denominator, 2 times 1 is 2. 12 divided by 2 is 6. So we end up with a positive 6 as our x-coordinate of the vertex. This is also the axis of symmetry. So the axis of symmetry is x equals 6. Now, to figure out the y-coordinate, we're going to take 6 and plug it into the function we were given. So we're going to say f of 6 equals 6 squared minus 12 times 6 plus 11. 6 squared is 36. 12 times 6 is 72 plus 11. 36 minus 72 is negative 36 plus 11 is negative 25. And that's our y-coordinate of the vertex. So we plugged in 6, we got negative 25 as the output. And that's all the information that we can get from the standard or general form. Now let's look at an example where we actually graph. Okay, so what are my suggested steps for using standard form and the intercepts in the vertex? Well, let me tell you. First of all, find the coordinates of the vertex. Use x equals negative b over 2a, then plug that into the function to figure out the corresponding y value. This will also tell you the axis of symmetry. Then you're going to find the x-intercepts by plugging in 0 for y or f of x or g of x or whatever the function's called. This will probably require factoring, and for this video, it will only require factoring. If the trinomial is not factorable, then you have to rely on other methods, such as completing the square or the quadratic formula. Then we're going to find the y-intercept by setting x equal to 0, or remember, because it's in this form, this standard form, it's just going to be that constant term. Then we'll use the axis of symmetry and the y-intercept to find another point on the graph. We'll talk about that when we actually see the graphs. Okay, so in our first example, we have this beautiful function, x squared minus 6x plus 5. The function's name is f. That's that italicized f in the beginning. We want to find the vertex, hk, and the axis of symmetry. Okay, so remember, for the vertex, well, first let's label. We have a is 1, b is negative 6, and c is 5. To find the vertex, to find that what I'm calling h, is we say x equals negative b over 2 times a. In this case, we have that negative, that's part of the formula. B is negative 6, and then we have 2 part of the formula times a is 1. We have two negatives, this one and this one, so that is ultimately going to become positive. In the denominator, 2 times 1 is 2. 6 divided by 2 is 3. This is the axis of symmetry, x equals 3. Now, the vertex, we now know that h is 3. What we don't know is that k value. We find the k value by plugging it into we plug in what we found for x into the function. So we would say f of 3, because that's what we got, equals, and now we substitute in 3 for all x values, 3 squared minus 6 times 3 plus 5. 3 squared is 9. 6 times 3 is 18. And then we get negative 9 plus 5, which is negative 4. I plugged in 3. I got an output of negative 4. That would be my vertex. Next up, let's find the x and y intercepts. The y-intercept is going to go a lot more smoothly, so say it with me now. The y-intercept is 0, 5. 0, 5. Let's find those x-intercepts. The x-intercepts, we're going to plug in 0 for f of x. We say f of x equals 0. So we get 0 equals x squared minus 6x plus 5. We know a is 1, b is negative 6, and c is 5 because we've already used it, well, all three of those variables already. So we know the target product here. Target product will be a times c 5, and the target sum, b, is negative 6. The winning combination here will be negative 1 and negative 5, which we can just plug right in, courtesy of a being 1. all the shortcuts for us. So we have x minus 5 and x minus 1. Once it's in factored form, now we set each factor equal to 0. X minus 5 equals 0, so x equals 5. That's the ordered pair 5, 0. And this one, x minus 1 equals 0, we would add 1 to both sides and get x equals 1. That's x is 1, and our output is 0. Now we're going to put all of this information on the graph. So we now know 4 points of this graph. The rule of thumb for quadratics is you want to know 5 points, where one of the 5 is the vertex. So we had to get that 5th point still, but we'll get there. I'm going to start with the vertex 3, -4. 3, -4 is down here. I also want to use the axis of symmetry. So the axis of symmetry is not actually part of the graph, right? It's just guiding us, helping us with the graph. So I'm going to change its color so we know it's not actually part of the graph. And now we're going to graph these 3 intercepts. So we have 1, 0 is right here, and 5, 0 is over here. Now, this axis of symmetry. So what we see is that these 2 intercepts, they're on like the same, they have the same output, right? They both have the same y value. The 2 numbers that have the same y value will always be the same distance from that red dashed line. So we see this one is 1, 2 away, right? It's 2 away from that red dashed line. Well, this intercept is also 2 away. That's the idea of the axis of symmetry. So we're going to use that with the y. The y-intercept was 0, 5. 0, 5 is up here. We can use that logic again to get another point. We can say, okay, well, 0, 5 is 1, 2, 3 units away from the axis of symmetry. So now we're going to go 3 in the other direction. 1, 2, 3 here. And there we have that 5th point. There it is, 6, 5. I see you. And now this is a parabola. It's a nice smooth curve. Sometimes these can look like absolute value where it's like a V, but it's not. It's a U. It's a smooth curve. I'm going to do the best I can given this is so far over on my screen. Let's see how I do. I'm also going to erase this. There we go. Oh, I erased part of my line. Sad day. Nice smooth curve at the bottom. Bring it back up. All right, that wasn't terrible. Only moderately terrible, but we see it has the general shape and we have the 5 points. And now let's do one more example. I encourage you to pause the video and try this one on your own. Okay, let's see how you did. First up, I'm going to label A, B, and C. I have A is -2, B is -8, and C is -6. Let's use this information to determine the vertex and the axis of symmetry. So we use x equals -b over 2a to help us. And we plug in, we keep that negative because it's part of the formula. B is -8 and a is -2. So a lot of negatives here. Let's count them. 1, 2, 3. That means that the x-coordinate will in fact be negative. Then we want to clean this up. The denominator is 2 times 2, which is 4. 8 divided by 4 is 2. So we end up with, first of all, an axis of symmetry of x equals -2. And we now know the x-coordinate of the vertex is -2. To determine the y-coordinate, we plug in -2 into the given function. So we're going to say g of -2, and we have -2 times -2 squared minus 8 times -2 minus 6. Order of operations says we need to do this exponent first. -2 squared is +4. Still is getting multiplied here, but we'll deal with that. I can work on this middle term now. Negative times negative gives me +16, and then minus 6. -2 times 4 is -8. So we have -8 plus 16 minus 6. This would be 8 minus 6. That's going to be 2. So we end up with y-coordinate of 2. So we have -2x, 2y, right? We plugged in -2. We got a 2 as an output. A lot of 2's in this one. Let's see about those intercepts. For the y-intercept, we're going to go back to that original given function, and we're going to say, well, the y-intercept, that's when we plug in 0 for x, and we get 0, -6. So we have to use the original for the y-intercept. For the x-intercepts, this is where we plug in 0 for g of x. We say g of x, so we say g of x equals 0, and we get 0 equals negative 2x squared minus 8x minus 6. I have a lot of issues with this. First of all, I don't like when the first term has a negative of my trinomial. Second of all, 2, 8, and 6 are all divisible by 2, or, to make me happy, negative 2. Because this is an equation, and all 4 terms, including 0, are divisible by negative 2, I can use the multiplication property of equality and divide a negative 2 from each term. And that's exactly what I'm going to do. So I divide everything by negative 2. And then I get 0 equals negative 2x squared divided by negative 2 is x squared. Negative 8x divided by negative 2 is positive 4x. Negative 6 divided by negative 2 is positive 3. Oh, that's so much better. And now, for target product, target sum, A is 1, B is 4, and C is 3. The target product is A times C, which is 3. The target sum is B, which is 4. The winning combination will be 1 and 3. I can plug those right into my binomials because A is 1, so I get x plus 1 times x plus 3 equals 0. Then I solve each one. I set each one equal to 0 and solve. This one's going to be x is negative 1. This one will be x is negative 3. So now I have my intercepts. I have negative 1, comma 0, and negative 3, comma 0. And I'm going to fix my graph so that way we can actually see negative 6. And I'm back with a better graph. Okay, so let's graph everything. We have negative 2, 2 is up here. And I'll go ahead and draw in that axis of symmetry that we're going to use. Okay, and now I'm going to graph these intercepts. So I'm going to start with the x-intercepts. I have negative 1, 0, and negative 3, 0. Just double checking. They look like they're the same distance from that vertical line. That's a good sign. The y-intercept, 0, negative 6 is down here. Let's find another point. I want that 5th point because I only have 4. This is 2 units away from that vertical line. Let's go 2 in the other direction. There we have it. Negative 4, negative 6 is another point. And we're going to connect these with a nice smooth curve. So even though I talked about it in the beginning, but I didn't really talk about it here, that A is negative 2. The given A was negative 2. The negative means it should be opening down, which it does. And the 2 means that and it does have a stretch, right? It's a little bit stretchier than the last graph that we saw. So it all kind of, the checks and balances are in place here. These have been examples of sketching graphs of quadratic functions using standard form, the vertex, and the intercepts. Thank you for stopping by.